Hello everyone. In our previous videos we've been talking about covalent bonds. And we know that covalent bonds are when you have valence electrons that are being attracted to two different nuclei. So two different nuclei of two different atoms are attracted to the same valence electrons. And it's that mutual attraction for the same valence electrons that holds the atoms together. So, picking up with that thought, when two atoms are bonded by sharing electrons, the electronic density, and electronic density just means where the majority of the electron's charge is mostly, the electronic density between them might not be equally shared. So that is to say, one nucleus may be attracting those electrons more than the other nucleus is attracting them. And we have a scale that reports this unequal sharing, and it's called electronegativity. Electronegativity, all one word. Electronegativity is a scale that reports the ability of an atom, and specifically the atom's nucleus, to attract the electrons in a covalent bond. So if we go up to previous examples, this is an example of a covalent bond between two iodine atoms. So these electrons are being attracted to that nucleus, and they're also being attracted to the nucleus of that atom. So these shared electrons are being attracted to both of these atomic nuclei. In this particular case, because the atoms on each end of that bond are identical, they would have equal attraction to those shared electrons. And so we would say that the electronic density of those two electrons would be evenly shared or equally distributed on both of those atoms. However, if you have a situation where you have two different atoms that are bonded in a covalent bond, those atoms may attract these electrons with a different degree of attraction. And so we're going to use electronegativity to report the atom's relative attractive force for the electrons in that bond. So I've given you a table here of some elements and their electronegativity values. And there's a general trend. The general trend is that electronegativity increases as you go up and to the right. In the periodic table. So if we look at our periodic table, we can see that generally as we go up a group and as we go right across a row, we increase the electronegativity of the atom. And fluorine is given the highest value because fluorine has the highest attraction for valence electrons when it is in a covalent bond. And we do not have electronegativity values for our noble gases because they generally do not form covalent bonds. So that means that fluorine has the highest electronegativity, and the trend is that electronegativity increases up and to the right. So the closer you are to fluorine, the higher your electronegativity is going to be. So on this chart, I've provided some of the electronegativity values. And I want to point out that these values are approximate only. If you actually look up the electronegativity values for these atoms online, you will find that they deviate slightly from these numbers. And the reason that I've given you these approximate numbers is that they have been rounded to make it easier for you to remember some of them. And you don't have to memorize all of them, but there are some that I would expect you to know. And the first one is hydrogen. I would expect you to know the electronegativity value for hydrogen. And then this row right here. I would expect you to know those: boron, carbon, nitrogen, oxygen, and fluorine. And then I would expect you to know that the first three noble gases do not have an electronegativity because they do not form bonds. So we've got hydrogen, boron, carbon, nitrogen, oxygen, fluorine, and then helium, neon, and argon. So now that I've shared with you the ones that I expect you to know, let's look at the pattern here, and you'll see why I have rounded these numbers. If you recall that fluorine is the highest electronegativity, and it has a value of 4.0, and then you lose half a point every time you take a step back in the column. So we go from 4.0 to 3.5, to 3.0, 2.5, 2.0. And you can remember that hydrogen has a value that would place it right there, just higher than boron. Boron's 2.0, hydrogen's 2.1. So fluorine is 4.0, then you lose a half a point every column that you take a step back until you get to boron, and then hydrogen is a tenth of a point greater than boron. And the first three noble gases should be easy to remember that they do not have electronegativity values because they do not form bonds with other atoms, and since they do not form bonds, it is impossible for them to have an electronegativity. Because remember, electronegativity reports the ability of that atom to attract the electrons in a covalent bond. So if you never form a covalent bond, you have no electronegativity. So down here at the bottom, why do you think no electronegativity is shown for some of the noble gases? They do not form bonds. And if you don't form bonds, there is no way for you to have an attraction to electrons in a covalent bond. So now with those electronegativity values, we are going to consider the types of covalent bonds that you can get depending on the differences in the electronegativities of the atoms that are bonded. So if bonds are formed between the same kind of atom, for example, the same atom here, they are identical atoms, so we have a bond forming from the same atom type, or between two atoms with electronegativity values that are different by less than 0.5 units, then there will be no significant difference in their electronegativity. So what does that mean? If we have two atoms that are bonded together, for example, like carbon and hydrogen, if we look at their electronegativity values, we see that carbon has an electronegativity value of 2.5, hydrogen has an electronegativity value of 2.1. The difference between them is 0.4. That is the difference in their relative electronegativity, which is to say that is the difference in their relative ability to attract electrons in the covalent bond between them. So if we have a carbon bonded with a hydrogen, then the difference in their electronegativities is 0.4. So it falls into this example. If the differences between their electronegativities is less than 0.5 units, then they are close enough in electronegativity that there will be no significant difference in their electronegativity. And therefore we say that the electrons, or the electron density, will be shared equally. Now in reality, there's going to be a little bit of unequal sharing, but as long as the difference in their electronegativities is less than 0.5, we go ahead and say that the electrons are shared equally. And if you have the electrons that are shared equally, the bond is called nonpolar. It's a nonpolar bond, and that means that neither end of the bond has more electron density than the other. So let's think about what the word polar means. When you have something that is polar, it means it has two poles, like a north pole and a south pole, like the magnetic field of the Earth or the magnetic field of a magnet. If you have something that is nonpolar, that means that it does not have two electromagnetic poles. That means that there's even distribution of that electromagnetic density, with neither end of the bond having more electron density than the other, non-polar. So in our example down here, we have carbon bonded to a hydrogen. So the carbon has an electronegativity value of 2.5, and the hydrogen has an electronegativity value of 2.1. And you will need to be able to memorize those values so that you can, when you see them, you can do the math. The difference between those values is 0.4. And you can see, therefore, that the difference in their electronegativities, they differ by less than 0.5. And therefore, this bond is called a nonpolar. And all of these are covalent bonds, so we would say that this is a nonpolar covalent bond. Okay? Carbon-hydrogen. When they bond in a covalent bond, the bond is nonpolar. There is an approximately equal sharing of the electron density between the two atoms. The electrons are not being pulled toward one atom more than the other atom. So in this case, we had two different atoms, but their electronegativities differed by less than 0.5. In this case, we have two identical atoms. So we know that regardless of what the electronegativity of the bromine is, we don't even need to know it in this case, because we know that the difference between the electronegativity of that atom and that atom is going to be 0. If we were to look back at our notes, we weren't required to memorize this one, but we can see that the bromine's electronegativity is 2.8. And so we can say 2.8 minus 2.8 equals 0.0. And we can see definitely that 0.0 is less than 0.5, right? But when they are identical, they're the same atom, same kind of atom. We already know without even doing that math that they are nonpolar bonds. So I've given you one more example, and obviously it's in this section, so you know the answer is going to be nonpolar covalent, right? But in this case, we have a phosphorus bonded to a hydrogen. So I would like for you to calculate the difference in their electronegativities, and based on that, determine that it is nonpolar. Now, phosphorus is not one of those atoms that you were expected to memorize its electronegativity. But you do have the value here on the previous page, so you can refer to it here for this problem. So go ahead and do that, pause the video, and when you're done, resume the video, and I'll work through this problem. All right, coming back to this problem, we have the electronegativity for phosphorus, which we look up on our chart, and it is 2.1. The electronegativity for hydrogen, which we should memorize, is 2.1. And we see in this case that the difference in their electronegativities is 0.0, which is less than the 0.5 cutoff, which means that these atoms form a nonpolar covalent bond. What does nonpolar covalent bond mean? A covalent bond means that there is a sharing of valence electrons, and the nonpolar means that this sharing is more or less equal. Now let's move on and take a look at some examples of when we get unequal sharing of valence electrons. So it says here, but if the difference in an atom electronegativities are anywhere from 0.5 to 1.9, then it will result in unequal sharing. They're still sharing electrons, it's still a covalent bond, but now it's going to be an unequal sharing because the difference in their electronegativities is 0.5 or greater up to 1.9. This type of bond, where we have unequal sharing of electrons, is called a polar covalent bond. And what does polar mean? It means that we have a north and south pole, and functionally it means one end of the bond has more electron density than the other. So the electrons are being drawn toward one atom more than they are to the other. And the way that we can graphically represent this or illustrate that we have a polar bond is to use dipole arrows, D-I-P-O-L-E arrows, and I'll show you what those look like in just a moment, and partial charges. Okay, so if the difference in the electronegativities of the atoms, and this is the difference between them, right? If their difference is 0.5 or greater up to 1.9, then we have an unequal sharing of electrons. The bond is still covalent because it's still sharing, but now it's unequal sharing, and that creates a polarity to the bond. And the polarity to the bond means that one end of the bond has more electron density than the other. And we're going to use dipole arrows and partial charges to illustrate it. So here I have an example, an oxygen-hydrogen single bond. So let's calculate the difference in their electronegativities. If we are memorizing these, then we know that the electronegativity for oxygen is 3.5, and hydrogen is 2.1, and so the difference between them is 1.4. Well, this does fall into this polar covalent bond category because 1.4 is 0.5 or greater up to 1.9. So we do have a polar covalent bond. And there is going to be unequal sharing of the electrons in that bond. They're going to be pulled toward the more electronegative atom, which is oxygen. So when we have an oxygen-hydrogen bond, those electrons are not being shared equally in that bond. They are being pulled toward the oxygen more than they are being pulled toward the hydrogen. So I'm going to represent that. I'm going to draw my oxygen and my hydrogen, and there's my bond, and I'm going to draw a dipole arrow. And a dipole arrow is an arrow that points in the direction that the electrons are being pulled. So the electrons are being pulled toward the oxygen. So a dipole arrow is drawn parallel to the bond with the arrowhead pointing in the direction toward the atom that is more electronegative. So we're showing the electrons heading in that direction. And we have a very important distinction here for dipole arrows. We put a little crosshatch on the tail of the dipole arrow because if electrons are being pulled toward that end of the bond, then the electronic density and the negative charges on the electrons in that bond are being pulled toward the oxygen. Then that leaves the hydrogen with a slightly positive charge on it. And so we put that little crosshatch on there to indicate that this end of the bond over here is electropositive because it has a little bit more positive charge. Okay? So that's a dipole arrow. So dipole arrow is there in red, and it shows the direction that the electrons are being drawn. It shows the polarity of that bond. Now, the other way that we can show the polarity of a bond is by using what's called partial charges, and I'm going to do the partial charges in green. A partial charge is not a full charge. So I'm going to use the convention, the notation that we use is a lowercase Greek sigma. It looks kind of like a D, only the top of the D is swoopy, or you might think of it as an S that loops back around on itself. That's a Greek lowercase sigma, and that sigma means partial charge. Now, if the electrons are being pulled toward the oxygen, that means that this end of this bond has a partial negative charge on it. And that means that this end of the bond must be partially positive. So both of these ways, the way in red and the way in green, are different ways to represent a polar bond. The red is the dipole arrow method, and the green shows the partial charges. Okay, so that's an example of when we have an uneven sharing of electrons in the bond. So it becomes a polar covalent bond because of the uneven sharing. So I have two other examples. I would like for you to do the exact same thing that I did here for both of these examples. So I would like you first to calculate the difference in their electronegativities so that you know that this is indeed a polar covalent bond. The double bond is not significant for our calculations of electronegativities. All we have to consider is that this is a carbon bonded to an oxygen. So do the math and then state that this is a polar covalent bond because you'll see the math. Then draw the bond the way I did here, and then draw the dipole arrow to show the direction that the electrons are being pulled in, and the partial charges to designate which end or which pole of that bond is partially positive and which is partially negative. Do that for both of these examples. Pause the video, and when you're done, resume the video and I will work through this. All right, coming back to this, we have carbon bonded to oxygen. If you're doing your memorization, you should remember that oxygen is 3.5, carbon is 2.5. So we have a 3.5 minus 2.5. And it doesn't really matter which one we put first, because we're basically just looking for the magnitude of the difference. So yes, if you put carbon first, 2.5 minus 3.5, you would get a negative value, but the negative is irrelevant. We're just looking for the difference between them. So the difference between them here is obviously 1.0. Does that qualify this as a polar covalent bond? Yes, it does, because it is 0.5 up to 1.9. So this is a polar covalent bond. So I'm going to draw the bond. This happens to be a double bond, but that doesn't matter in this case. The dipole arrow is pointing toward the more electronegative atom, which in this case is the oxygen. So the dipole arrow in this case is going to be pointed that way with the little crosshatch over here on the carbon end. Partial charges, I need a partial positive down here with the carbon, and a partial negative at this end of the bond with the oxygen. Moving on, we have another example here. We've got nitrogen and hydrogen. Nitrogen has an electronegativity of 3.0. Hydrogen has an electronegativity of 2.1. And we can see that the difference is 0.9. So is this polar or non-polar? It falls in the range from 0.5, including 0.5, up to 1.9. So this is a polar covalent bond. Which is to say that the electrons are not being shared equally in that bond. So I draw the bond. And now let's draw the dipole arrow. It's going to be pointed toward the nitrogen because nitrogen is more electronegative, with a crosshatch down there at the hydrogen. And the partial charges, nitrogen gets the partial negative because it has the electrons being drawn toward it. And hydrogen is the electropositive because it has electrons being drawn away from it. And there we go. So there we have examples of non-polar covalent bonds where the electrons are being shared equally or close enough to equally to call it equal. And we have polar covalent bonds where the electrons are not being shared equally. And so then we have a polar bond, and we can show the polarity of the bond either with a dipole arrow or with partial charges. Okay, well then this raises the question, what happens when you have two atoms that are trying to bond with each other and the difference in their electronegativities is greater than 1.9? Well, that's what this last part is down here. If the electronegativities are very different, and the difference therefore is 2.0 or greater, then they are no longer satisfied energetically to share the electrons. At a 2.0 electronegativity difference or greater, one atom has such a great thirst for the electrons that the electrons are going to be stripped away and transferred from the less electronegative atom to the other more electronegative atom. And when you strip away the electrons completely, you are no longer sharing them, so you no longer have a covalent bond. And then you form ions. And if you have ions, then you form ionic bonds. So if the difference in the electronegativities is 2.0 or greater, you no longer have a covalent sharing of electrons. It's no longer even satisfied to share them unequally. One atom is going to completely strip the electrons away from the other atom, and when you do that, you form ions. So here are some examples. I've got sodium and chlorine. If I look on my chart, sodium has an electronegativity of 0.9, chlorine is 3.0. So 3.0 minus 0.9, and we see the difference in their electronegativities is 2.1. Well, that's 2.0 or greater, so this chlorine is so much more electronegative than the sodium, it is no longer satisfied in simply sharing the electron pair. It's going to strip the extra electron away from sodium so that chlorine doesn't have to share an electron pair with sodium. So basically you will get a sodium that has lost an electron and the chlorine that has stripped it away and gained it. And so we have ions, and then we have the electrostatic attraction between the ion charges, and that is an ionic bond. So here we have another example. I would like for you to do the same thing that we did here for this. Notice that I'm not going to draw a bond between the two atoms when there is an ionic bond, because there is no shared pair of electrons between them. So I end up just having the two ions that are sitting next to each other. So what I have done right here, I would like for you to continue on and do that for lithium nitride. So pause the video now and do that, and when you're done, resume the video and I'll work through that. Okay, coming back to this, lithium nitride. So we've got lithium has electronegativity of 1.0, nitrogen is 3.0. So the difference, 3.0 for nitrogen, minus 1.0 for lithium. And it doesn't matter that you've got several lithiums there. We're looking at the relationship between the nitrogen and a lithium. The difference in their electronegativities is 2.0, so that hits the 2.0 threshold for the electronegativity difference. And now we can see that the nitrogen is not going to be satisfied by sharing an electron pair with lithium. It's just going to strip an electron away from the lithium. And so I'll get a lithium cation and a nitrogen that takes on an electron, strips away an electron from each of three lithiums, and becomes the nitride. So I get ions, and I get the ionic bonds. And we know in both of these cases, when you have ionic bonds, ions with ionic bonds, we have ionic compounds. So just to review, we look at the electronegativity differences, not the electronegativity values themselves, but the differences. And if the differences in the two atoms that are bonded is less than 0.5, then we say that they're being equally shared and we have nonpolar covalent bonds. If the differences in electronegativities are as large as 0.5, so there's 0.5 or greater up to 1.9, then they are still satisfied sharing the electrons in the bond. It's just that they're not going to do it equally. And so that gives rise to polar covalent bonds. And we can show the polarity of the bond, that is the direction in which the electrons are being drawn in the bond, either with the dipole arrow or with partial charges. And again, these partial charges do not represent a full ionic charge because we do not have an ion here. We have a covalent species. But one of the atoms is taking on a little bit more electron density and it's pulling it away from the other one, leading to those partial charges. And then we have the case where the difference in electronegativities is so great that one atom is not going to be satisfied sharing those electrons anymore, and so it's just going to strip an electron away, and then you'll form ions and you'll have an ionic compound.